Hi everyone. This is now topic 6C and topic 6, and we're going to be talking in this case about measurement and calculation of heat, or remember that the symbol for heat is lowercase q. In the previous set of videos we talked about how to calculate and measure work, and remember that when we add heat and work together we're going to get our delta E, which is the change in energy of a reaction, and that's the quantity that we're trying to measure and calculate in this case, because it tells us something about how the molecules in the reactions behave if we're able to get that number, the delta E number. So we're now going to spend some time talking about heat and various aspects of heat calculation. The first thing to remember about heat, of course, is that by definition is the energy transfer that occur when two systems, or the system and the surrounding, have different temperatures. As a result, energy is transferred from the system that is at higher temperature, in other words, the hotter system, to the system that is at lower temperature, the colder system. And from experience, you probably have seen this many times over. If, for example, you go into a cold room, over time you feel a little colder because heat from your body constantly is being released to the surrounding, the room, and then of course if you're going into a room that's hot, over time you feel hotter because heat from the room is constantly coming into your body because you are at a lower temperature, so the heat from the higher temperature will come in, the energy from the higher temperature will go into your body because your body is at a lower temperature. So this happens for all kinds of systems, and the energy transfer will occur continuously until both systems reach something called thermal equilibrium, which really just means that the temperatures are the same. Now, if you don't have any, let's say you have two systems, and the two systems are insulated, and so then the one system is at a higher temperature, the other system is at a lower temperature. And the system at a higher temperature is releasing energy to the system at a lower temperature. If no energy is lost to the surrounding, then basically at the end, because of conservation of energy, the energy released by one system has to equal the energy absorbed by the other system. And because the energy is in the form of heat, we would just say heat released by system 1 must equal heat released by heat absorbed by system 2. And because release of heat or release of any energy is denoted by a negative sign, you would say negative of Q1 has to equal to positive of Q2, which is the absorption. Okay, so this is an important thing to keep in mind later on when we're going to do calculations of heat, because if you think about it, when you have two systems where one is releasing energy, the other system must absorb exactly the same amount of energy. So one of the things that, if you think about heat, because heat is energy transfer as a result of a difference in temperatures, we would then expect that the amount of heat that is transferred from one system to another would be proportional to the change in temperature that happens. In other words, if you have a bigger temperature change, you should get a bigger amount of heat transferred, larger amount of heat transferred. And if you have a smaller temperature change, then you have a smaller amount of heat transferred. So this symbol here is a proportionality symbol. It just says that the amount of heat transferred must be proportional to delta T, which is the change in temperature. Now, of course, we don't usually operate with proportionality, but we usually operate with equality. So then the question is, what would make this proportionality become an equation? We change this to Q equals to C times delta T, where C in this case is what we refer to as the heat capacity of the substance, and that's just a proportionality constant. If you think about it, it's really just something you can measure it experimentally. It's something that makes this equation work for a particular substance. Okay, so you can rewrite this as C equals Q over delta T, in which case then it's something you can measure experimentally, because if I were to heat, if it takes me 100 joules of energy to raise the temperature of a substance by 1 degree Celsius, that means that the heat capacity for that substance is 100 joules. If For another substance, it takes me 1,000 joules, then the heat capacity for that substance is 1,000 joules. Okay, so that's kind of a way this constant can be determined. All right. Let's talk a little bit more about heat capacity. As we just said, heat capacity is the amount of heat needed to increase the temperature of a substance by 1 degree Celsius. Now, you can also say that it's the amount of heat needed to increase temperature by 1 Kelvin, okay, 1 degree Kelvin. Because remember that the Celsius temperature and the Kelvin temperature have the same conversion factor, right? There's no, an increase in 1 degree Celsius is the same as increase in 1 Kelvin. And this is really something you should kind of work out on your own, on your notes, to think about a little bit more carefully. You should realize that that's true. Now, as a result of this definition, right, which comes from this equation right here, which is that C is equal to Q over delta T, the units that we have for heat capacity would be joules, unit of energy, divided by degree Celsius, if you're using degree Celsius, or joules over Kelvin. That will be another possible unit. Calories over Kelvin is another common unit you'll see a lot in older textbook. Calorie over degree Celsius, another common unit, okay? Heat capacity by definition is the amount of heat needed to increase temperature, so it's always a positive number, right? It's the amount, how much energy it takes to increase the temperature of a substance. Now, if you think about the heat capacity quantity itself, okay, let's say I have two, I'm just illustrating this in two size, rectangles, but let's say I have two containers filled with water, okay? So this is all water in here. And if you think about it, by definition of heat capacity, it's the amount of heat needed to increase the container of water by 1 degree Celsius. By experience, you can tell that if I have this much water, it's for sure is going to take more heat, right? More energy in order to increase the temperature of this container of water by 1 degree Celsius compared to the amount of energy that will take to increase the temperature of this container of water by 1 degree Celsius. In other words, it will take more energy to heat up this water to the same by the same increase of temperature, because there's more water here, right? There's more mass, there's more molecules, which means that it will take more energy to make all that water go up 1 degree Celsius. As a result, if you think about it, the value of C, right, the value of heat capacity, changes depending on mass, okay, or depending on really number of particles, right? So if you have more particles, you get a larger C. If you have fewer particles, you have a smaller C, which means that heat capacity is an extensive property. Remember, we talked about extensive and intensive property early on in the semester. So this is clearly an example of an extensive property because its value changes as a function of mass. Now, a lot of times people don't want that to be the case, because when you're making calculation, you'd rather take that mass component out, and you want to just compare the value of C for different substances and see if you can have a more fundamental understanding of why the C of a particular substance is a large number and C of other substances are a lower number. So then we come up with this two additional quantities related to heat capacity, and they're called specific heat capacity and molar heat capacity. And both of these are basically just the intensive variation of heat capacity. And what do I mean by that? What I mean is that specific heat capacity is just defined as the heat capacity divided by gram of material, 1 gram of material. So the heat capacity per gram of material. So in other words, what you do is you just take that number and divide it per 1 gram of material. In other words, you just say, okay, I just want to take 1 gram of material and see what that value of C is. Now, if you divide the quantity to 1 per gram of material, then if these both are water, then the two numbers have to be the same, right? Because now you're expressing it per gram of water. So in other words, you're now making something that's extensive to become something that's intensive, okay? Because then the numbers become the same. It's independent of mass at this point, okay? So that's what specific heat capacity is. It's the unit, of course, is then becoming unit of energy, joules per gram degree Celsius, or calorie per gram degree Celsius. So again, compare that to the unit of heat capacity, which is joules per degree Celsius without the gram, okay? You can also express this as molar heat capacity, which is yet another way of making it an intensive property. In that case, you would say molar heat capacity is heat capacity per mole of material. Okay, so then in this case the unit is joules per mole degree Celsius or calories per mole degree Celsius. So the difference between these two is just one is expressed per gram, the other one is expressed per mole. Now, the type of heat capacity you have to use to solve a problem really depends on the context of that problem. Sometimes you're going to use specific heat, sometimes you're going to use molar heat capacity. Okay, in certain textbook this is given a symbol C S, okay, C sub S, and then in other textbook this one would be given the symbol M, C sub M. So I would just highlight this here as subscripts just so that in case you see this in the future you'll be aware of it. But the heat capacity symbol itself is just C, and then specific heat sometimes you see it as C sub S, and then molar heat capacity as C sub M.